Hello and welcome to this portion of the Getting Started with Wave video series. I'm Dr. Matthew Wang and I'm a practicing optometrist in Irvine, California. In this section of the video series, we'll address orthokeratology lens design and is not meant to be viewed first. So if you have not yet watched the single vision and multifocal training video, please pause here and watch that video before proceeding, as the upcoming principles build on what is presented in the other clip. If you are ready to move on, here's what we're going to cover next. After a brief introduction, I'll review qualitative and quantitative assessment of baseline topographies. Then I'll share some principles related to topography selection and reasons to reject specific topographic images. Following that will be manual editing and cleaning of captured images. And finally, extrapolation, measuring HVID, and evaluating the spherical offset map before designing the lens. This section of the video series will conclude with the actual design of a Wave OrthoK lens. In this segment, I'm going to highlight some of the basic elements of a baseline topography that I evaluate when considering a patient's candidacy for orthokeratology, as well as some of the mental notes I like to make before actually designing a lens for the patient. Now keep in mind that this entire video series is for patients who fall within the VST guidelines for OrthoK, and that's up to 5 diopters of myopia and 1.5 diopters of astigmatism corrected with a corneal lens. But many of these principles will still apply in case you're treating a patient with different refractive errors or perhaps with a different lens type. On the screen right now are 4 single eye captures from 4 different patients, and each has at least one element that could be a potential challenge to a smooth treatment regimen, but really none of these patients have any outstanding topographical anomalies that automatically disqualify them from OrthoK. It's the subtleties that we'll encounter a little bit more often than the glaring problems, and I'll try to point out some of these more common ones that I see, starting with the map on the upper right. So the first thing I do is a gross evaluation of the capture. We can see that the upper lid is plainly visible, some lashes, and then there's this area of steepening right next to that, and that's almost certainly artifact. Down below, we see a little bit of the lower lid, tear meniscus writing above it, which is also introducing some artifact into the computed data. So there are times that a better capture just isn't possible, but this probably should not be the type of capture that we default to for lens design. In the top left, we have a little bit less upper lid showing, but you can see these islands of varying curvature kind of sprinkled throughout the entire topography without any distinct pattern to them. And this appearance is real common with patients with a short tear breakup time. It's a good idea to treat the ocular surface, then capture new topographies before starting OrthoK. In the lower left, we can see that all the lid structures are pulled out of the way, which is fantastic. Of note, in this area down here is a little bit of steepening that's not reflected up above. So there's some toricity in this cornea, but it's not symmetrical. And so in my mind, I'm thinking this is probably going to be a freeform design rather than a GSIM, as asymmetry either between the upper and lower halves of the cornea or the nasal and temporal halves of the cornea is really the key factor in determining what lens design to go with. And finally, the map on the lower right shows a fairly regular and symmetrical cornea. No lids or lashes are visible. All we have is a little bit of artifact down below. This is probably caused by the reflection of the lid margin that the camera is picking up during the capture, but this can be edited out before we even design a lens. One other observation to take into account, especially if you're treating adult, is pupil size. Designing an OrthoK lens for a child for the purposes of myopia control is going to be pretty different from designing a lens for an adult where we're trying to maximize vision and even in low light situations. So, for example, this pupil down here in the lower left is going to be a lot more susceptible to flare and glare when it's dark, when this patient is potentially driving at nighttime, if this happens to be a patient that's going to drive at nighttime. So being aware of pupil size, again, is going to be something that you want to key in on before designing lenses. After the initial gross observation, I'll take a quick look at some numbers, primarily SIMK, toricity, and eccentricity. All these maps have k-values that are fairly regular. The map in the upper left has probably the flattest central sim-k. It might be more of a challenge in case the patient is pushing up against the upper limits of the VST guidelines, but really I'm looking to make sure we're not dealing with a patient with Ks in the 30s or 50s, which again may not be an automatic disqualification from OrthoK, but it's great to be aware of this information before giving a final recommendation to the patient. Eccentricity is represented in e-values, and most people will fall between 0.4 and 0.6. Anything outside of that range will give me a little bit of pause, such as this patient in the upper right corner, where in the flat meridian the eccentricity is a little bit low. And then finally I'll take a look at corneal toricity. Mainly I'm just looking to see right now how much agreement there is between corneal toricity and cylinder power in the patient's refraction. So this initial survey gives me a pretty good idea how smoothly I can expect treatment to go, and allows me to better set expectations both for myself and for the patient before we even start OrthoK. In this segment, I'll go over how I determine which map to use for the patient's lens design. I always capture anywhere between 4 and 8 maps per eye and run a repeatability check to make sure that all the data I got is consistent. So here in this window we can see that we have 4 maps that correlate with one another quite well. These maps showing on the screen right now all look pretty good. No adnexa in the way, normal appearing tear film, and although there is this unusual area of steepening in the upper nasal quadrant in each of the maps, I think I'm ready to go ahead and look at the photo process view of each of these maps to make a final determination. What I normally do is bring up the first 2 potential maps in photo process view and then do a comparison. I want to use the topography that shows the most rings, the most complete rings, and the sharpest rings. So in comparing these 2 images, it appears that the capture on the left side is just a little bit more stable than the one on the right. The one on the right shows a little bit of jaggedness to the edges of the rings, down especially around this area. And so I'm going to disqualify this one and just close that window out. So the better of the 2 maps is still here on the left side. I've opened up the next one, and again this one compared to the one on the left, just a little bit more rough around the edges, and so I'll close this one out. And I'll do this 1 against 1 process of elimination until I'm left remaining with my one best map. So assuming that we go with this map on the left, everything looks pretty good. My only potential concerns might be we have some reflections of the lashes above and a little bit of below. And there's also a little bit of bleed right here in between these 2 rings, but a lot of that is going to be editable, and I think this would be a pretty safe topography to use to design a lens for this patient. My next step would be to go on and edit this map, but before doing that I'll show some examples of captures that are a little bit less than ideal, ones that I might hesitate to use for lens design. They'll have elements that'll show up in your captures from time to time, and generally we want to avoid these whenever possible. So here in the top left corner we have a map where we can see a lot of shakiness in the rings. In the top right we have a lot of lid structures in the way. Same thing as the bottom left, a lot of lid structures in the way. And we can see that this capture was taken quite a bit off center, where there's a lot of ring data that's not even captured within the frame of the topographer's photo. Some of these we might have even rejected before getting to this step. And then finally, we can sometimes see that rings can be broken in some parts of the topography. So all these elements can make your case a little bit more challenging, and these are things I would try to decide against when deciding which map to build a lens on. In this segment, I'll go over the last few steps that I go through before designing a lens for the patient, and that would be editing the rings, deleting portions of rings that we don't need, extrapolating the map, measuring corneal diameter, and then also looking at an elevation profile to decide what kind of lens design we're going to use. The capture we're looking at right now is a little bit less than ideal, quite jagged, And if we enter the dots editing mode, we can see that there are lots of areas where we can manually smooth out the data. But smoothing out the data might leave us with a topography that's not true to life. And so really we don't want to, even though we can edit a map like this, we really don't want to use it for lens design. If we instead have a map that looks pretty clean and smooth, the dots editing process is actually really easy. We can move out quite a bit and see that there isn't much data that we need to smooth out until perhaps we get to the very last few rings. So a small area here, small area here, and that's about it. At this point, I'm going to delete some of the data that we don't need. So this flat area up here looks like it's artifact. This part that's bleeding onto the conjunctiva we don't need for a corneal lens. And then this area of steepening right next to the tear meniscus, or the reflection of the lid. So go ahead and turn the rings on and erase a few segments here. So now we're left with data that's more even and more regular all the way around. The next thing we do is extrapolate the map, and this is not any different from the way I would extrapolate for a non-OrthoK case. So generally we just want to center the Myers within the extrapolation circle that we draw. From here I'll go ahead and measure corneal diameter, and I measure from the edge of the gray to edge of gray. In this case, about 11.1 millimeters for this cornea. Right now is a good time to save your map. Don't forget to save your work along the way, and within the save window you can control click or right click on the map you just extrapolated, and Scout software will give you an option to mark that map as your best one. Also, there will be a tab where you can enter the patient's spectacle correction, and if you have that saved within the Scout software, then when you design a lens in Wave, Wave will pick up that information and automatically transfer it over. And the last step is to look at the spherical offset map, and this will help us determine whether we're going to use a G-SIM or a freeform or perhaps an R-SIM lens for this patient. The spherical offset map takes an imaginary sphere with a radius of curvature, in this case of 8.09 millimeters, and lays it on top of this cornea. And the warmer colors are where the cornea actually rises above that reference sphere, and the cooler colors are where the cornea is lower than that reference sphere. So just overall, with a qualitative assessment of this cornea, we can definitely see that the vertical meridian is very different from the horizontal. And so that tells me that we're at least going to use a G-SIM lens where the vertical can be made different from the horizontal. With more detail, I'll look at about 3.5 millimeters out, and we can see that we're about 9.8 microns at this point above the reference sphere. If we go to 3.5 millimeters out on the other side, we can see we're about 26 microns above the reference sphere. So with this patient, the nasal part of the cornea is a little bit taller than the temporal part of the cornea. And there's a difference of approximately 17 microns at a distance of 3.5 millimeters away from the center. So anytime I get a difference of more than 10 microns, I start leaning towards the thought of using a freeform lens. If we look at the vertical meridian, 3.5 millimeters out, we're below the reference sphere by about 8.2 microns superiorly. Inferiorly, we're below by about 2 microns. So that difference is less than 10 microns, but because of the difference we have in the horizontal meridian, I would go ahead and use a freeform lens for this patient. In this segment, we're moving into actual lens design. The design process for VST OrthoK is pretty straightforward because a great majority of the patient analysis is done prior to this step. We've already evaluated quality of baseline topographies, selected a best map for editing, measured HVID for overall diameter determination, and then looked at the elevation map to decide whether we're using an RSIM, GSIM, or freeform design. So once a new lens is generated from the Scout software, this is the first decision we have to make within Wave. And for OrthoK, I generally choose to not average the astigmatism data. And if you save the patient's refraction within the Scout software, you'll see that it auto-populates here. But if not, no problem, just use the drop-down menu to enter the appropriate numbers. And now to turn this lens into an OrthoK lens, we'll go into the Tools menu and choose Configuration Settings. And we'll see that VST OrthoK is one of the built-in presets that can be downloaded from Wave. These default parameters work pretty well, but you can always use your own values if you want. And if there are specific values that you would like to use as your own default, then you can just enter them here. And then you can rename this default. And once you save it, then these default parameters you can select from the list for all your future lenses. The one value that we will have to regularly change from default is going to be the overall diameter. And I like to use a diameter that's about 0.2 millimeters smaller than the HVID we measured. I personally design in axial mode, and for this lens I chose GSIM. This first box is for RSIM. My screen resolution just has part of the R cut off. The Wave software now presents us with the initially designed lens, and we can see the predicted tear layer across the entire cornea in this meridian underneath the lens. This is where we can make some final adjustments. For example, I may decide to loosen the periphery a little bit to reduce our central clearance. And then once we've made your final changes, of course, don't forget to save your work. At the top, you'll see the note that this is a lens for a patient that falls within VST guidelines. And so this particular lens does qualify for Wave's lens warranty program. And this brings us to the end of the video series for Wave orthokeratology lens design.